4 pi epsilon r square unit vector along r in the sense. This is what is to be written for the unit. You want the vector. Of course, that AR you already down here. So unit vector AR, this is x axis, y axis. So then go to theta here. So unit vector AR the same as 1 times cosine of theta along AX plus 1 times sin theta along AY for 2 XY if I want to write it this way. But you can say unit vector because how do you write a unit vector? AR dot AR unit vector AR. This I don't teach you. You are supposed to be able to know all these things. I just review it because I find out a lot of people very shaky foundation. AR dot AR give you AX give you cos squared plus sin squared. Right? You multiply AR dot AR, AX dot AY is 0, AX 1, cos squared theta is 1. You have to say unit vector. So I don't know how you got maths, I don't know. Okay. So AR squared, the modulus is AR dot AR cosine of angle between AR and AR, 0 because of 0 to 1. But we know that unit vector and region is 1. So you have done so many people have problems on vectors, 0, this thing means you have not grasped all this foundation. Okay, let's move on further. Of course, this is only valid for planar XY coordinate system. XY, plane. When you have XYZ, this is not valid. XYZ coordinate system unit vector will be 1 sin theta cos phi along AX plus 1 sin theta sin phi along AY plus cos theta along AZ. The XYZ coordinate system. And this is only for 2D form. This one will be better than me, you learn what you do. Let me write it down because I don't want to go all from off. Okay, so this angle is theta. This angle is phi. So therefore, unit vector, so AR is given by 1 times sin theta cos phi on AX plus 1 sin theta sin phi on AY plus 1 times cosine of theta on AZ. So this is for 3D. So for 3D, you can find out this is a unit vectors. The phi angle phi. You can check also that the modulus of AR is 1. Unit vector what? You can check what? You're copying this, so if you didn't know this. Anyway. Okay, so in the 3D dimension, 3D, 1 sin theta cos phi from X. Here, sin theta cos phi. 1 sin theta sin phi along Y. 1 cos theta along Z. That's it. can be used. You can check the unit vector is 1. You take AR dot AR, you find is 1. Okay, this one is for this research. So just now we saw that the picture of lines of field, quite useful picture. For instance, if I have a field is very strong, okay, like the iron filings here, the stronger the field, the denser the iron filings sticking out. So what happens is that if you have, so those of you who know about semiconductors on top of your house, like very sharp point here. So what happens? The clouds, they charged up, and the cloud is charged up. Near the point, the field is very high, discharges, and then it all goes down. So therefore, if you got the small region here, you find that it's like that. So point here. Okay, of course, this is connected to ground. So the cloud is very charged up, very, very strong cloud. So what will happen is that the field will be created here, very, very high. Here, not so high. So the field is very high, and then the point where it causes a breakdown of the air becomes ionized, and therefore they conduct. So electrons from here will flow and neutralize these positive charges. Otherwise, the house catch fire. So you can see from this picture here that here the field is strongest. The density is very high. Density of the lines per unit area is very high. That is why when you look at the field plot, where the fields are weakest, the lines are less dense, usually the field is weak. Near the charges here, the field is very strong. If you're very far away, if you take say the same area, unit area, there are more lines crossing unit area in space. So that's why you look at the picture. The more lines you see per unit area, the stronger. This is just an interesting, very useful picture or representation of the field. Now, if the density is constant, for example, a parallel capacitor with zero fringing, and the field density is zero. But a parallel capacitor, when the spacing is large compared to the D, not so small, and in the center of the capacitor, it is uniform, and outside the more dense. Fringing field. So the experiment, those who do the module of the experiment each and one, they will observe this plotting. Okay, so we move on now. We move on now to look at the new concept of using field. So we saw force. We saw force. And then we say force per unit charge. Force per unit charge. Test charge. We call this electric field E. Electric field vector. Vector. Okay. But what happened is that electric field is a vector. It would have been desirable if we can have something which is scalar. Okay. It is possible in this field. So far we haven't desired yet. But first, this is electric field going on here. E is electric field, volts per meter, electric field, force acting on unit test charge placed at that point, and stop repeating this charge. But now we have a new concept of electric flux density vector. I will explain to you now. Now for D. So you have E and D. But of course the question is, why do you want to introduce all this kind of new concept? You want to introduce new concept because they obey slightly different laws. In certain cases it is simpler to use D than E. So the question is, if I calculate E directly, the vector, more work. But if I calculate D, I can exploit something called symmetry. Having found D, the question is, what is E? Very simple. Tell them D equal to epsilon naught, epsilon R times E. So in other words, if I find D, I can find E by dividing by epsilon R. So I want to tell you now, epsilon naught is 8.854 times 10 minus 12. Okay, current per meter. Epsilon naught has no dimension, no units. It's called dielectric constant. So having found D, I can find E. The question is, why do I find D? I find D because you should see very soon it is causes a lot of signification. Now, for example, I give an example first before we carry further. If I have a big fat moral charge, or radius A, very big, it's not a point, very big. I want to find the field at point P here, P, at the distance say of twice A and twice A, R prime. I want to find EP. So, using the method we have told you now, the field is going to be obtained by putting a test charge of +1 there. No change, still the same. No change. So I put the charge of +1 there. This is not the point. I have to chop into small volume. The whole charge is Q. Okay, charge is Q. So therefore density rho is given by Q over 4/3 pi A cube. This is just a substitution. Coulomb per meter cube. So the total charge is Q. So the charge density is Q over 4/3 pi A cube. Coulomb per meter cube. So now I have known this given to me. And given this A, I'm given to A. Calculate EP. Not so simple, right? So you write the first equation, the first expression, delta V. So the first expression, EP, dEP, the vector, P. Small element here, you can see is pointing this way. This is dQ, is rho dV. Rho dV times 1 as usual over 4 pi epsilon r square. This is r here, directed here. dEP. I write it down. Don't forget, it's the vector. It's the vector UR here, AR here. It's going this way. Now I scan over the source, the next small volume. R changes. I go to the next one here. The angle changes. Everything changes. So this is a very fantastic job, you know. Very difficult to do. Very difficult. By the method which we have been telling you. Put a charge of +1 there. Calculate the force coming up from a small volume of charges and sum vectorially all those forces. That's a lot of work. What do you say? You are thinking aloud or you are saying a question? You don't think aloud because you confuse me because I thought you are asking something. So think quietly in your own mind. Because something solid that you ask. Because you think aloud is very disturbing. Right, because I don't know what you're asking a question, you're making a statement, you're asking a question, I'm not sure. So therefore we don't want any probability of 50%. We want something sure. Either you ask question or you don't ask. Okay? So therefore this problem is very difficult to do. Very complicated. Cannot do. Not cannot do. It's a lot of work. So but then if you use the concept of D, new concept, you can see this model takes on immediately by inspection. By inspection, it will be feeling like a spectre. Bus conductor, inspector, check your ticket. Tell you the ticket. That's it. Okay, by inspection, you can using the new method. So the new method is based on flux density, flux. So what is flux? Flux is the amount of thing that flows, flux density. For example, the light coming from this projector, if I take unit area, the intensity of the light, the amount of light crossing this unit area divided by the area given. The light flux density. So much, so many watts per meter square gives me some flux density. So similarly, the same way you can see that if you use this new concept of flux density vector and exploit the symmetry of the source, you can solve this complicated problem just like that. Okay. Alright, okay. Then let's move on. Before we talk about how to solve this kind of problem, let's look at the basic foundation. So this idea of flux was introduced by Mr. Michael Faraday, very famous British scientist, physicist. Unfortunately, he died very poor because all his discoveries were stolen by his boss. Everything he discovered, his boss did. His boss was a very rich guy. He preserved all his findings in the Royal Society. So he couldn't get anything. And we were just a kind of Java academic society. Okay, so now to talk about the idea of flux, we did the experiment with flux. This is going to lead us to Gauss's law, Mr. Gauss. So what happened is that if you have a charge of Qi inside here over some conductor, ball, consider a ball, and then this is surrounded by another ball, another shell, and that shell is grounded. Grounded means connected to the wire to the ground. Now, whether something is grounded or not makes a lot of difference. Makes a lot of difference. Let me just be simple to practice. If you have a ball of charges, okay, so if you by itself, positive charges will exist, electric field will exist. Isolated, nothing touches it. But if you allow it to be grounded, the potential of this thing drops, potential goes to zero, the ground, the electrons from the earth will fly off, electron will neutralize this. So therefore the ball becomes neutral, no more field. If you neutralize the charges, there is no more field. So here, no field. Grounded. After grounded. So in practice, when people lay cables, high power cable, anything, they always have to ground the outer conductor. Why? But you can see from here, why? If this is my inner conductor, let me assume it is a cylindrical conductor for simplicity. Okay, positive charges here. Okay. So if I put the outer conductor C, the outer conductor is here like that, I have negative charges here. So inside here, inside the, assume it's air between, you have electric field going on, negative, positive, negative. When this is negative, is outside here, you have something also outside here, because there are negative charges here. So therefore, your system is not isolated. But if you ground this, you neutralize all the charges on the outside, leaving only charges outside. Right? So you can see, let me do it again. Positive, negative. Not grounded yet. Positive here. Because the outer conductor was neutral initially. Middle conductor, here you have electric field pointing this way. This is direction. But then if you ground this, electron from the earth will go and neutralize the outside. Neutralize all these funny charges here. Outside. So therefore you can see there will be no field outside. So let me draw this again. Now after grounding, positive occur no change. Again, negative. Since you have grounded this, the outside has disappeared, charges, inside the field is still there. The field inside the two conductors is still present, but outside there is no stray field outside because you have grounded. Because electrons from the earth will go and neutralize any charges on the outside, because remember, by the charge neutrality, plus Q, minus Q induces plus Q, and there's another minus Q at infinity. Because the total charge in the universe cannot change. So plus Q, outer conductor minus Q, the inside of the conductor, minus Q, conductor was neutral outside there, minus Q, plus Q. Plus Q minus Q plus Q, there's an extra minus Q missing, and minus Q infinity. That's what the field ends up at infinity. So now if you ground this, nothing left there, the field inside is confined there, the field is still there, but nothing outside. So that's important, the ground. Okay, now going back to this. Suppose I have Qi here, assuming I have grounded the thing, all the positive charges have been taken off, so I have a minus Q here. So the plus Q is on the surface of the conductor, and minus Q the inner surface of the outer conductor, and outside there is nothing. Because already when I do the grounding, it kills all outside charges. So now, obviously inside there are fields. So by conservation of charges, Qi is minus Q naught. This is Qi, Q naught will be minus Qi. I told you. If you create Qi, you must have Q naught, but Q minus Qi. So in other words, you can put this as Qi minus Qi inside it. So Faraday thought of this idea and he said, look, sounds very interesting because the electric field will be going from positive to negative, and he says it's as if there's some kind of displacement, some kind of movement or the flux from the inner conductor to the outer, from the outer conductor, from the outer surface of inner conductor to the inner surface of the outer shell. It's the idea. Flowing, of course it doesn't flow, it's just the idea. That's why it's called flux. Okay. And the flux is the same as charge. In other words, the flux coming out of Qi, say is phi. Flux reaching there also phi. So in other words, look at the second picture now. If I have a small element delta Q, it will end up with minus delta Q, so therefore there is a flux flowing from plus Q to minus Q. So the cube of flux actually doesn't flow, it's just an idea. That's why the idea of flux. Flux comes from the English word flow, flux, flow. Okay, now. And then he says, look, whatever is flowing, as also flux, is the same as the charge. In other words, the flux has got the same as the flux, the same as the charge, and the same units. So flux is same as charge. Okay, now, if I take the flux and divide by area, I get flux density. And since flux is the same as charge, flux density is Coulomb per meter square. Right? Okay now. So the flux has got the same units as charge. The flux density is charge divided by area. In this case here, if this is delta Q, the area is delta S, then the flux density will be delta Q over delta S. And let's now look at the next picture which makes things easier. So this idea of flux is the same as charge, and got the same units. Flux is the same as charge. You see how nice it is. Same picture again. Conductor, grounded, nothing outside here. Electric field is going from plus to minus. So according to class conservation, a flux also is conserved. In other words, whatever is coming out of the plus Q is preserved for any radius. At the radius of R1, it is plus Q by flux. And the radius of 2R1 is still plus Q, and so on and so forth. So the flux is conserved. You can see that light. If I draw a surface here, the amount of light that crosses this closed surface is the same. Because the surface gets bigger and bigger, the flux is the same, but the density gets smaller. The flux remains the same, but as you go further away from the source, the flux density drops. That's very interesting. Now, if you look carefully now, flux coming out of the plus Q is Q, as we said before, in the inner sphere. Okay, and it will come out for any radius R greater than A and less than B, the same. In other words, the flux is the same coming from here. Therefore, at any distance R, the flux will be, then R is going to A, the flux density will be total flux plus Q over 4 pi A squared. The area of surface of the sphere is 4 pi R squared, 4 pi A squared, 4 pi A squared, in the sphere. So for any arbitrary distance R greater than A less than B, is Q 4 pi R squared. And of course R is going to be exactly here it is Q over 5 or 4 pi R squared. So this idea of flux being the same as charge, you can see it going to be right, very easy. So we saw just now, we had a big fat charge, divide a small element delta V, put a charge of plus 1 down there at the point P and so on. So suppose now we want to calculate what is the field at the point P here inside it. Suppose at the distance of R, find EP. It's a very difficult problem, you know. I have to chop, add all the positive contribution at this point P, start the plus 1 there, chop all the negative charges and add again and get the answer, and that will be the field. But that method is too complicated, too involved, because now if you look carefully at this picture now, you can see that for the same distance of R, distance from plus Q, for any angular orientation, for the same distance of R, so long as I keep the R constant, the value of the field will be the same. The value of the flux density will be the same. And at the given distance of R, the flux density will be Q over 4 pi R squared. If I keep R constant, the value is followed. Every R I keep the same, but of course the field will change direction. It doesn't matter. I want the value Q over 4 pi r squared. So everywhere for the same R, the flux density is the same. What field presence? So Q over 4 pi r squared will point in on R. Okay, now. So now if I find out what is D, as I told you is not, D and E are related to here. So if D is Q over 4 pi r squared, then E is the same as Q over 4 pi r squared divided by epsilon r, or epsilon r is the property of the medium inside this configuration. But of course, you can see the dominant assumption here is that we have symmetry, spherical symmetry. As we go from here, we do this, we go around the same distance r, the value of the field is the same. Agree? But it's symmetrical. What is symmetrical? What is symmetry? If I ask you what is symmetry, can you explain what is symmetry? It means that for a given distance r inside there, you take any angular orientation as you go the same way as r, you will also always see the same value of the field, but of course the direction will change. We want the value the same. So we have symmetry, spherical symmetry. You will see now symmetry plays a big part in simplifying problems. Okay. So therefore, now at a given distance of r, I can find what's the field, what's the D, density. I will find D, I can find E because E is simply equal to D over epsilon r or Q over 4 pi epsilon r squared. Same distance, same vector AR. Okay? And let's now look at the next picture, which will make things a bit easier to understand, easier to grasp. So remember, to apply the idea of flux, I must have some symmetry, otherwise I will have a problem. But most things in life are symmetrical, so it should be okay. Let's look at this picture, next picture. Now we're going to see how we can calculate a simple case of a point charge. A point charge of value Q, calculate the field at point P, where P distance of R. But that's no problem because this one not complicated, there's only one source. Put the test charge of +1 here, the field here is Q times 1 over 4 pi epsilon r squared, 4 pi epsilon r squared, finish already. That's the answer. But now we want to use the idea of flux to show you we get the same answer. A point charge has a spherical symmetry. Why? Because a point charge is a sphere of small radius. It's a sphere, very small radius. So therefore, for a given same distance r, as you go around the small point charge, the small sphere, the value of the flux density is the same, everything the same. Therefore, I can find the flux density is Q over 4 pi r squared. Charge, flux, charge, total flux is charge, Q over area. Area of the sphere surface is 4 pi r squared. Therefore, I want to find electric field. D and E are connected to epsilon r. If this is air, epsilon r is 1, I get this. So I see here, this is the answer. But of course, we must have, although D and E are always related to epsilon r, the idea of flux is a symmetry, flux density. If you have no symmetry, the method is still valid, but you cannot get a simple answer. Definitely, you can. Are you with me? Are you on board? Anybody thinking or floating so far? Floating. Okay. So this is the expression that you know. In general, it is this: D epsilon r that E. Okay. So epsilon r is known as dielectric constant, capacitance. Dielectric permittivity of free space, epsilon r is 8.854, given to you, -12. Epsilon r got no units. Epsilon r got no units. For example, dielectric constant of water is 81, epsilon r. Dielectric constant of perspex is 2.2. Dielectric constant of FR4, PCB material is 4.1, and so on. But of course, you may ask the question, what's the importance of epsilon r? You've done capacitance in your lower years, I don't know where. Because the epsilon r will allow system of conductor, you have two power plate, you are dielectric in between. The larger the epsilon r within the plate, the more charge you can store. The more charge you can store means you can build a larger capacitance. And capacitors are used in RF circuit for push-pull tank circuit, oscillator, iPhone, everything. Okay? So therefore you can see this simple problem here. This point here is a sphere. I can calculate the field, this is simple. I can find the electric field using simple method, plus 1, Q times 1 over epsilon r squared. But the idea here to show you that when you have symmetry, you can use idea of flux density vector D. So now let's go to the problem which I told you very difficult to solve. Okay. This is the complicated monster here. Volume is rho, whatever it is, calculate upon P. Very complicated. But now, because we say that at a given point P, R, instead of R here, if I go around, okay, I have symmetry. The volume will be the same. So therefore, this allows me to exploit this symmetry. In other words, you can see now, this is how we do the problem. This is my wall of charges. This is rho, coulomb per meter cube. Total charge is Q. The area is A, and the radius A. Therefore, rho is 4 pi 4 squared by A cube. Coulomb per meter cube. Okay. So the fourth thing is the ball of charges. Ball. So the problem was how to find the electric field at the point P here. Okay. At the instance of what? So if we do not explore the symmetry, what will happen is that we see problem. Chop, 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 delta V, rho, all these vectors will keep on changing direction. Can't do. Can do after many hours of work and mistakes, I got no answer. But as I said, if I take a given distance R, I go the same distance R, I go round. Okay, on the surface of the sphere, I will see the same value of the field. Of course, the field will point in different direction, but the value is the same. So, therefore, using the idea of flux, the total flux, I draw a big sphere, enclosing this one, I have the total flux, the same as Q. Here, the flux charge. Therefore, the flux density D is flux upon area, the same as Q, 4 pi R squared. This is R. Directed of R. So therefore, simply equal to G over epsilon naught epsilon r is 3 over 4 pi epsilon naught epsilon r squared. That's the answer. So this complicated mesh problem cannot be done. It can be done because of symmetry. Symmetry of charge or source. Whether something is symmetrical or not, the key parameter, key thing to consider is the source. If the charge is symmetrical thing, the field will be symmetrical with the surface. By the way, this surface of radius r is called a Gaussian surface. That is not it. According to this Gauss's law, called okay. So symmetry. Of course, if I have a cube has no symmetry. Right? Look at this bottle of water here. If I draw at the center of the water, I draw a big sphere on it, symmetry. And I go here, I see different aspect of the source. But if my source is a long infinite line source, and I use cylindrical coordinate and radius of r, I go around, I see the same thing. I see symmetry. Provided I use the right coordinate system. Right? A cube will have no symmetry. However you do, always see one corner, one side, so there is no symmetry. Okay, everybody, agree? Like this one here. If I look here, I see this face. I look here, I see this face. I look on the side, I see the corner. So there is no symmetry. Whenever I have a ball of charges, wherever I go for the same radius, I see the same thing. Focus, concentrate. Okay? So therefore I can solve it very easily because of symmetry. So therefore this leads us to something called Gauss's law. Look at Gauss's law, last slide. So Carl Friedrich Gauss, who did come up with this law? In the finished tomorrow, you go back or tomorrow what we're talking about. If you have any question, you can come and ask me. So that you can carry on further. Don't go back and introduce you, then forget about it, come back next time. Observe. Passive learning. Okay. So you have a point charge here, something called Gauss's law, related to electric flux. As we said before, if I draw a closed surface on this slide, at a given radius, small radius, the flux the same, but the effect is stronger than when it is further away. So the flux the same, total flux the same coming out of the source, the charge, but depending on this surface enclosing the charge, the further you go, the radius r become larger and larger, the area become larger and larger, so the flux density falls. Okay, so now if you look at this point charge here, if you look at surface S1, which is here, surface S2, which is in different place. So whatever be the surface shape, doesn't depend on the shape. The main thing is that it must be closed. If the surface is closed, then of course you catch all the light. For example, if I draw a closed surface, the amount of light coming through the closed surface is the same as if I make the surface smaller. But I cannot leave the surface half open. Nonsensical. Right? Closed surface. The surface is closed, meaning completely surrounding. So now, irrespective of the shape, same. Whether I draw a elliptical shaped surface, or spherical surface, or a box surface, the amount of light crossing the surfaces at 90 degrees is the same. The conservation of flux. Like a water going in a channel. Whether you block it with something which is at an angle, or straight, or circular, the amount of water that goes through a given surface is the same. So the surface must be closed. So therefore, Gauss's law says the electric flux passing through any closed surface is equal to total charge enclosed by the surface. This is flux. Flux. So Gauss's law, in the book sometimes we mistakenly refer to as the law of fields. It is not. Gauss's law is the law of flux, electric flux.
Look what that one when
so after net charge here is this. Look at the word here. Electric flux, total electric flux, passing to any closed surface is equal to total charge enclosed by the surface. Total charge here, net resultant. Sorry, the word net. Resultant. Resultant of net. Let me get an example now. So this is a this is a point charge of Q plus Q. Okay, so if I draw a closed surface to it, so for the sphere, I can go sphere. The amount of flux that crossing the surface here, phi plus Q. We say flux is the same as charge.